around and say, oh, we should have a meeting and somebody should talk. There's a lot of infrastructure work that's gone on, getting the food and the setup and whatever. And so we certainly want to thank Shelley for being here. We have a small flower and something that maybe will make your Friday evening a little nicer.
Whoa, thank you. Thank you, thank you, thank you.
And you want to say something?
Oh, do I want to say something? You know, this is my third Keck Science meeting. I never used to come to them before. The pandemic happened and we had to figure out what to do. And so we went completely virtual and that was a breeze, you guys, I have to tell you. And then when we came back and we did San Diego last year, I've never done anything so hard in my entire life. But so we do need to figure out where we're going in the future. But I think it's so important for us to be here together in the same room, that you all get to collaborate and meet each other and see each other face to face. So I really am pushing to move this to a completely in-person meeting in the future. So any support we want to provide for that, talking to your bosses or your instructors and mentors, that would really help a lot. So I thank you for being here, for taking the time out of your busy schedules and your dissertations and all your paperwork that you're doing right now. But this is super important for you to be here, and I hope you make a ton of great connections. And I will see you next year. And thank you so much.
There's been other people that are also instrumental in this.
Yep.
And O'Shea's been on the video, and maybe you can name a few other people.
Yeah, so at Keck, who they didn't get to come, I really wish they could have been here because it's important for you to meet them as well. Megan O'Shea, who's our executive administrative assistant, she's Hilton's admin. So she's done all the catering for us, so all the food and the drink and the lunch and breakfast, that's all Megan. She's also been helping with lodging and doing a lot of behind the scenes coordinating. So hopefully at some time you'll get to meet her. We also have 3 brand new admins that we're helping with Zoom room coordination for our breakout sessions. So that's Lonnie, Elaine, and Naylin. And then we also have Lori, I think, who did one session. She's Ed Harris, who's our fund development guru back there, and Joan Campbell, our other fund development guru. She serves as their administrative assistant. So there's a ton of Keck people that support you, right? We support you folks, and we would love to see you in person at headquarters, because then you can meet all these people that, you maybe see only an email from them. And this is how it was for Devin and I. I've seen his name so many times, and I finally met him probably 4 years ago. And I was like, oh, this is the Devin. And then I met the Demogod's dad, and then so you develop these relationships that you have forever. So I really hope to see, like I've said, hope to see you here, hope to see you in Hawaii, and come look us up, come stop by and visit.
And the other elements of this is, I think you've also seen some instrumentation and pictures. I know a lot of you like download data or get data from your advisors or things like that. And I think seeing the videos of the instrumentation or some of the talks that we've had, and we'll see more now of future instrumentation, like getting a connection with everything that has to happen at Keck in order for photons to hit detectors and images to go places and papers to be made. It all part of this meeting is the science, but it's also kind of connecting different parts of our community that don't necessarily get to meet otherwise. The other person I need to acknowledge is Stevie McLean, who's local here at Caltech and has helped with lots of local things, assisting people at Keck. Also in charge of, I'm not sure exactly who's done what, and she also has with you. Thank you. Thank you, Sally.
Yeah. So for all the different Keck Science meetings we do, it's every other year it's here at Caltech, and then it's at a UC school. And so having someone on the ground here locally is completely invaluable, because I don't know what this room is and who to call for security. And so Judy's the magic behind the scenes. She gets the stuff done. I said, Judy, I need this thing, and she goes, got it. So Judy's been completely instrumental in this meeting.
You're welcome. And has done this probably maybe your 10th Keck Science meeting.
All right, since we're embarrassing people, I have to embarrass Lynn, and where's Mom? Yeah, yeah, because, you know, they've been absolutely instrumental in setting up the science program, setting up the SSC stuff, coordinating the other SSC members, because Lynn shouted out the other members of the SSC were here, but didn't shout out herself. And didn't shout out Juan, so I'm going to, so please, you can all give them a round of applause. And like Joey said, even though we're trying to reduce our carbon footprint, we really do love it when you visit us. So please consider it at some point, or at least figure out a way to find your favorite your tech person and ask them to bring 3 of their friends onto the Zoom to talk to you about any of the stuff that we can about. Thanks.
Okay, onward, science and
Science.
participation.
Yeah,
So Lauren, here's the last.
Okay, after all this love, let's go to science again. Before you leave, if you want to keep this, you can, but if you just want to throw it out, just leave it on the table so we can recycle it. And Tony, coming. So we have Antonia Rodriguez from Caltech telling us about X-ray mixed the optical and magnetic cataclysmic variables with Keck.
You need to be by the microphone and the L in specific. I need to.
Thank you so much.
Mhm.
Perfect, thank you. Just forward, back.
Yep.
Okay.
Okay.
Hi, everyone. I'm Tony Rodriguez. I'm a grad student here at Caltech, and I'd love to start by thanking all of the Keck staff and all the instrumentalists who helped build the instruments, contribute to the data pipeline. Just, anyone who works on Keck and making it possible. It's really awesome for me to, go up to my friends, family, and say, hey, I use the world's biggest telescope made possible by, 10 of other people who shoulder them building up. So I'd like to start by thanking everyone. I'll talk to you about something a little bit different. So I'll talk to you about binary stars. Oh, not stuff. Cool. Oh, cool.
I wish.
Yes. I'll start talking about binary stars and why this rather niche subset of them is actually really interesting. Quality alert, all spectra are going to be really good because they're all Keck spectra used in this talk. If you can spot the ESI spectrum, I'll give you a bonus afterward. There's actually one ESI spectrum. Okay, so that's the rough overview of my talk, and I'll begin by telling you about the discovery machine and the discovery algorithm that I've sort of put together for these rather niche systems. So I begin with this Wiki Transient Facility, which is the deepest northern sky survey, and it really is a predecessor to Rubin LSST, which has been promoted by the Hadal survey, promoted by a lot of science as being very big in the next decade. And you can see here why that science is possible. ZTF has a huge field of view, and in 2 days it can scan the whole northern sky. Just to give you a sense of what these filters look like and what the ZTF camera is like, here it is compared to Roger Smith, the lead engineer's head. And the reason that this table is so important, I'm highlighting what's most important about this. It's this 20.4 mag. So once Rubin LSST comes online, that's going to go down to 24th magnitude, and we really need Keck. We really need these big telescopes. Obviously, there's going to be, TMT, GMT, those big telescopes in the future. But right now, it's really a good time to probe how deep we can go and how much we can supplement these surveys. Because as much as we can get out of a light curve, getting spectra is really what we need. And that's what Keck is there for. We need Keck algorithm for follow-up. So now into the science. Most sun-like stars are actually like Tatooine, so they're binaries. And single star evolution, we have graduate classes on it. I learned the HR diagram, where stars move, where they begin, how they end. But binary star evolution is a lot richer. You get a lot of astrophysical laboratories in the process of having binary stars. And it's also important because binaries lead to so many interesting things that a lot of other astrophysics builds on. They lead to explosions, which then serve as standard candles, kilonovae, which synthesize heaviest elements on Earth, gravitational waves. I've been told that to get more funding, we need to say multi-messenger astronomy. So that's another plus right there for binaries. But my question is how do they evolve on the way to get to these phenomena? So there's a lot of sort of cartoons that you have for binary star evolution. Most of them involve these two. So they involve things that are unknown, like the common envelope phase. They involve what actually happened in type 1a supernova phase. But I study some intermediate processes. And some of those include a lot of unanswered questions in magnetic fields, common envelope evolution, what actually is able to come out of that. Basic questions in angular momentum loss. How do you bring two stars closer together? And what's really unknown for a lot of these subsystems is what the distribution is and what their occurrence rate is in the galaxy. So I'll begin with my current favorite subset of binaries known as cataclysmic variables. And most simply put, these are systems where a white dwarf accretes from a main sequence star. In some cases, it might be helium rich. This cartoon, although just a cartoon, is actually very representative of what these systems are. You have a star that's undergoing Roche lobe overflow. It loses mass through a stream. It hits a bright spot, gets onto a disk, and through loss of energy, it dissipates its way into the boundary layer, into the white dwarf itself. And these are optical variables. That's how I find them in ZTF after scanning the sky. They're variable because they're binaries that revolve around the center of mass. There's accretion. You have magnetic fields that can be present. I'll explain later why that can lead to optical variability. But something that I've picked out from ZTF is that it's a huge data set. So we need to sort of, focus in a little bit, find out what's really interesting within that large data set. And these are X-ray sources. So if I begin with the X-ray and then look at ZTF through that, I can find these systems. In this subset that I'm showing you here, these are non-magnetic cataclysmic variables. These have been found for a long time. In this case, the X-ray comes from friction at this white dwarf disk boundary layer. I'm much more interested in these much more exotic systems known as magnetic cataclysmic variables. In this case, the X-rays come from the material, the accreted material, slamming down onto the white dwarf surface, which then leads to a shock. And this shock is then what leads to X-rays that we observe. The reason that these magnetic CVs, as I'll refer to them, are so interesting is because they have amongst the strongest magnetic moments of any binaries in the galaxy. They're actually stronger than magnets are if you look at the magnetic moment. The field is not strong, but the moment is. Nonetheless, these fields can range from 1 to 250 megagauss. Sounds about 1 Gauss, so that's many orders of magnitude, 10 to the 7 stronger than it. And what's been really interesting about these is that their number has been grossly underestimated. If you look at papers in the 90s, it was thought that maybe 5% of CVs were magnetic. In the mid-2000s, it was 25 to 35%. But right now is a really great time for stellar astronomy because we have Gaia. And with a Gaia volume-limited sample, the most recent study found that almost 40% of these are magnetic. I still think that number is underestimated, and finding more of these and understanding how these play a role into CV evolution is really important for understanding these models, again, how the stars evolve all the way down to spiraling and giving explosions. Also, the origin of these magnetic fields is unknown. It's got 3 competing theories, but so many weird systems keep popping up that need to be explained by every new theory that gets put forth. So understanding is having a good volume limited sample of these is really one of my main goals, one of my main hopes. But how do we discover these? So as I said, I rely on the X-ray as an initial cut. And what you're seeing here, you'll see those blue points, which are tiny and very hard to see. Those are all of the X-ray sources and some small patch of the sky from our latest and greatest X-ray survey from 25 years ago, ROSAT, 1990. So it was a great survey. Actually, 40% of all the sources in ROSAT they still don't really have an optical counterpart. Happy to chat about that later and what I've been doing to help alleviate that. But we now have another X-ray telescope. Don't ask me if it's working or not, if it's still up. I can't tell you that. But there was a public data set released from the Zeta Space Telescope. And that is what the galactic sky looks like to this X-ray telescope. So I scanned this data set and pulled out all the interesting galactic things that are within it. You see a lot of active just M stars toward the red side of this. This is really what I'm calling the X-ray main sequence. If you read from left to right, that's really just OVA FGKM. But for the more X-ray luminous blue things, those are all accreting sources. All the CVs pile up nicely up in the upper left corner. And not just that, the magnetic CVs tend to be much more X-ray bright. So those are actually at the top of that little cloud. So really, these are good tools to be building for supervised machine learning algorithms to pick out things in ZTF, to eventually pick out things in Rubin LSST. And as I said, we just need to get to the important systems. Okay, non-magnetic CVs, a lot of those have been found, and they've been found because of the light curve that you're seeing on the left. That's the light curve from ZTF. They undergo dwarf novae outbursts, and that's inherently a disk phenomenon. It's due to the H- opacity within the disk that leads to a thermal instability, and you get an eruption. But I don't know if you saw the cartoon of the magnetic CVs I have. The magnetic field pressure is so strong that it can disrupt the disk. So there will be either a really feeble disk in the intermediate polars or no disk at all. in the other subset of magnetic CVs known as polars. So they won't go outbursts, they won't undergo outbursts. So how do we find them? Just to show you again, for the non-magnetic CVs, they don't have a helium-2 line because they don't have strong enough X-rays to ionize helium. But it's harder to identify the magnetic CVs because they don't undergo outbursts. The light curves look something like this. There's just variability without having the outburst, but they're much brighter in the X-rays. So having the two data sets combined is what makes it so powerful for their discovery, and that's just why they've been missed in the past. There wasn't good enough, there weren't good enough X-ray data sets. And here you'll see very strong helium-2 lines. That's really the dead giveaway. There's kind of an empirical formula that you can use the equivalent width of the helium-2 line to determine whether the CV is magnetic or not. So in this paper that I submitted earlier this year, this is really the feature of this paper, and it's this eclipsing polar, and it stood out as a bright X-ray source in the C Rosita catalog. And that's some of the Keck spectra that you're seeing on the right here. So it's eclipsing, and what's really interesting to see in some of these is you can actually trace out the whole geometry of the system, because you're seeing the emission lines when you're looking at the accretion stream and you're looking at the donor star. But as the stream passes in front of the hotspot on the white dwarf, you can see some of those emission line inversions. So the Balmer lines get into absorption because you have something cooler in front of something hot, when normally in these systems, it's the other way around. So there's only about 6 of these that have been found. Of all the polars, of all the magnetic CVs, this is like 1 out of 6 that has been found. The more systems we get like this, the better we can understand what the geometry of these accretion streams look like, better we can understand how matter actually gets funneled down to the white dwarf surface. And I was able to get a whole orbit with LRIS on Keck. And this is really how we can understand the geometry of all these systems. What you're seeing in the light curve, and the reason that you're seeing the continuum go up and down so much, is because that's actually it's known as cyclotron beaming. Cyclotron beaming is just when you have particles going around the magnetic field of the white dwarf. You're seeing their harmonics in frequency space. So you can see that manifested in the optical wavelengths actually for these systems. Oh, it's not changing on that. Okay, you can make these awesome Doppler tomograms, which are basically decomposing all of that into velocity and phase space. You can really pull out, okay, that's coming from the accretion stream. That other bit, you're actually seeing the irradiated face of the donor star. What you can do with that then is you can build radial velocities. You can then understand what the masses are with the donor mass, with the white dwarf masses in these systems. You're seeing those lines split because one of them is due from the accretion stream, and the other is the irradiated face of the donor star. So pulling out all the geometry, we can then get to what we want. We want the mass of these white dwarfs, and this continues to support the fact that if you look at most white dwarfs that are in binaries, their mass tends to cluster around 0.6 solar masses. All the white dwarfs in CVs are about 0.8 solar masses. So this is thought to be due to perhaps something of common envelope evolution, where the lower mass white dwarfs are lost. But it's good to just continue to get more of these and understand the masses of these systems. There's a lot more interesting ones. Again, here's more of the cyclotron beaming that you're seeing here. These are all very faint sources, so it's really, really useful to have Keck for all of these. And I know I'm running out of time, but I'll just flash a couple more light curves and spectra. There's a ton more of these that are coming out of these searches, combining ZTF with X-ray surveys. I'm not stopping at that small Rosita field. There's a lot of data from XMM, Chandra, Swift, other X-ray telescopes. All the spectra, it's the same thing, helium-2, 4686. You're seeing, confirming that these are magnetic. Those are the cyclotron features. You can pull out the magnetic field estimate directly from where these bumps are located. So I'd like to thank people in my group that all helped facilitate, help for the proposals so that all this could be possible. Thank you to all the organizers of this meeting, all the Keck staff, all the people we built this telescope on. And I'll give you some quick conclusions and then flash the most interesting part of this talk. The first magnetic CV that is actually below the limit. Yeah, at least one of the questions too.
flat, so. Second here. What everyone think and.
Oh, there's,
Yeah, can you please explain this, perspective, this operation?
Yeah, so what I wanted to emphasize was actually how faint this source is. And this was also discovered through similar methods for finding these magnetic CVs. You can see there, so it's the optical magnitude, it's pushing 20.5 and 21st magnitude. And all that I want to do, so you can find the periods using ZTF of these systems, but to confirm that it's indeed a magnetic cataclysmic variable, you need that helium-2 line. I'm just highlighting the lines, and that's exactly what you're seeing here. With the full orbit, you can then see the cyclotron beaming. You can see what the magnetic field strength of systems like this, what it actually is.
Stare at the light curves in the upper right more than is healthy. It almost looks like the peaks shift a little bit between the ZTF and the camera data. Is that real?
Yeah, these systems can evolve over time. So what you can actually get is pole inversion, where you get more accretion out to one pole compared to the other. That's not what's happening here. It's just that the ZTF data covers a bit more time. So it probably evolved a little bit and the peak shifted a little bit. It's a little hard to see, but there are some red points behind that, behind the blue part of that light curve. But that's a very normal phenomenon that happens in these polar magnetic CVs.
So the ZTF is lots and lots and lots of months older than the camera data is just
One night as opposed to, yeah, 4 years.
7 all the states.
Exactly.
Maybe try liking the data years or something, and so you can actually see an evolution.
You can, before some state change. Yeah, it's cool. Yeah.
Okay, thank you very much.
Thank you.